Welcome back to the Max Runout YouTube channel, and this is our part 2 of our series on making gears automatically. In the last video we went through the steps of making a gear manually, and I have to apologize for the some of the video was kind of glary there. I have some very bright lights on the mill that shine right down on the part that I'm working on, which is good for my eyes, but the camera didn't like it much, so you got a lot of glare there. Some of the later pictures were better though, but anyway, you got an idea of how the gear cutter works and how it engages the gear blank, and how we got that done. So now, as I said before, I'm going to have to make thousands of gear teeth, so we definitely want to automate the process. So in order to do that, we got to replicate basically what motions I was making back and forth with the mill table. First of all, we'll need two motors, one to drive the mill table, move it back and forth, and that motor has got to have a modest amount of power, because the mill table is heavy, and what you have on it is heavy, and so there's a modest amount of torque required to move the table. And the second motor is going to be driving the rotary table, and that motor needs a ton of resolution. We're going to be making gears with 100 teeth, and you have to be able to get all the way around that gear with a very, very small amount of error, so that the tooth spacing stays even. And so I needed something with a lot of resolution. Now, the motors I settled on after thinking about it for a while were some units that were made by a company called Technic. They have been in the motor business for quite a long time, or motor controller and motor business for a long time. And actually, as it happens, the guys that started that company and still run it are fellows that I know pretty well. The business is only 30-minute or so drive from my place, and so I was able to connect with them and talk to them about what could be done. They got a new, fairly new product here. It's been out for a year or so, called a Clear Path motor, and the neat thing about that is it's a servo motor, and but it has all the motor control electronics are inside this little silver box here on the back of the motor. And this is a motor they make themselves. They're all built in the U.S., and it's something they worked on the design of for quite a few years, and it's a pretty amazing little box. If you want to, you can use it exactly like you would use a stepper motor. You send it steps, and it will make it'll turn its shaft to the amount of each step that you send it, depending upon how you got it set up, for how many steps per revolution. But it'll also work in many other modes. You can have a mode where you want it to move a certain amount and then stop. You can have things where it'll home itself automatically and then come back to the point that you want to start at. There's all kinds of ways that you can use the thing. I think there's 11 different modes, and they have a video on their website, that a separate video for each mode that shows how they all work. But the one model of the motor works just like a stepper motor, and you give it steps and it moves, and the faster you send the steps, the faster it moves. And of course, when you're not sending it a step, it's a servo motor, so it holds its position. And the other thing about it is that if somehow you got a big heavy thing on there and you send it steps too fast and it overloads it, the motor never forgets how many steps you sent it, so it'll never lose a step like a stepper motor will. But I decided I want to use it in a different mode. Another mode that it works in that's pretty cool is the what do they call it? It'll come to me in a minute, but it's kind of like a stepper, but not really. You send it steps, and you can send it steps as fast as you want. In my case, I'm actually sending it steps at frequency of about 100 kilohertz, and it remembers all the steps you sent it and then moves in a way that you program it to move. There's a little USB connector in the back here. It's covered up with a plug, but it's a USB connector in the back, and you plug that in there and you program the motor for the mode or whatever that you want, and then it'll operate that way. Like, for example, in this mode that I'm using, which is pulse positioning, it's called. You send it the pulses real fast, and then you program it through a computer you can plug in here for temporarily, just to program it and then take it away, to set the maximum RPM that it can go at, the maximum amount of acceleration it can have, and some other stuff. So and then it worries about all the speed and acceleration and that thing within this little box. So that's I decided to give that a try, and I'll be setting it up here shortly, and I'll show you how that worked out. Okay, here's my lash up for testing these motors. Over here is a power supply. The Technic guys do not recommend that you use a switching supply with these, because the motors tend to take power in gulps, and the switching supplies could temporarily go into current limit mode, which is not good, because then the supply voltage drops, unless it's, you know, rated for a much higher current. But they recommend you use just a simple power supply. This is just a rectifier and a transformer, a bridge rectifier, and a big lytic in the output, like this. It's 25,000 microfarad lytic, and I have one of those in the output of the supply. So and that's connected directly to the motor. So if the motor wants a big gulp of current, it can have it. So I just threw this together for powering the motors. The transformer I happen to have around only gave me about 30 volts of output, but that's enough to power the motor. They will run anywhere from 24 to 75 volts, and of course if you want the full performance you need to go up to 75 volts. But at any rate, this seems to work fine, at least the way the motors are lashed up now. And then over here I have the two motors. Well, only one of them is powered up right now, the one on the left, and I mounted the two motors on a little board because again, the Technic guys said that if you don't tie them down, they got so much torque they're liable to jump right off the table. So I mounted them to a little board, and that seems to work fine. I'm really not using them anywhere near their maximum output, so I don't think I'll have a problem. And then if you swing to the right here, I got my computer here. There's a USB cable plugged into the computer, and that's plugged into the back of the left-hand motor there. You can't quite see that, but and then the power cord, you can see, is plugged into the motor. So we're ready to go here. Okay, we're ready to run a test on the motors. The setup we just showed you previously. As I said, the one on the left is powered up. It doesn't have any control signals going into it, but it is plugged in through the USB cable to my computer, and you should be seeing the ClearPath software and the picture of the motors at the same time here. So anyway, this is the software that comes with the ClearPath motors, and I just take you a little tour through it here. First of all, I have it set in the mode. I have the mode set to pulse burst positioning, which is the one that I want to use. The first thing you want to look at is input resolution, as it's set right now for 800, which is plenty of resolution for the motor that's going to drive the mill table back and forth. We don't need a lot of precision there, just enough to get past the gear and make sure the cut is complete. And so 800 is more than enough. But for the other motor, we need a lot more precision, as much as we can get. And these motors have really got it. This is this motor here will go up to 6,400 counts per revolution. And so I have a 90-to-1 worm drive, and then another 2-to-1 drive in the pulleys that I've chosen. So that's a lot of resolution, more than 1,000,000 counts per revolution. And so I will certainly be able to get the resolution that I need to cut these gears. So we're just going to leave it set for 800 right now, and I'll get into some of the other things here more later, but the important thing here is you want to set the speed of the motor, and right now I got it set for 20 RPM, and which is probably in the neighborhood of what I might use for moving the table. It is a 2-speed device, so you have an alternate speed limit, which at the moment is set for 200. We won't be exercising that right now, but that's I'll be using a higher speed on the return stroke if we move the table to the left, or I'm sorry, to the right for doing the cutting, and then move it back again. I'll probably use a higher speed for that, but for now we're just running a test on the motor. So the other thing is the acceleration. You can set this wherever you want. I got it set for a pretty high number right now, but I'll go through that in a bit. And the other thing is the RAS. I can't tell you that I know exactly what that is or how it works, but I know it has to do with the way the motor accelerates and settles at the end, and you can set that to a lot of different timings. I have it set for 51 milliseconds now, which seems to work okay with the motors unloaded, but I don't know exactly where I'm going to have to set it eventually. Then the next layer is it shows all the inputs and outputs from the motor. The motor has 3 inputs, as I said in the no, I guess I didn't cover that yet. It has 3 inputs of the motor. The first one is the enable input, and these are ones you would normally control from whatever you're using to control the motor, a little microcontroller or something. And the first one is enable, and if you turn that on, if that's off, then the motor will freewheel, and you can see it's easy to turn here now. It has essentially no resistance, and so I can set it wherever I want by just twisting with my fingers. But when it's enabled, then it's in the servo mode, and then it should hold its position. The next input is the direction input. When that's input is true, then it goes counterclockwise, and when it's not true, it goes clockwise. So that's an easy one to understand. And then this input B is where you send your pulses, and then the other thing is an output, and they call that all systems go, but really for the purpose of what we're doing, it's motion is completed, basically. This output, will be true. Will be false while the thing is moving, and then will be true. I can't remember which way it is, but it'll be in one state when the motor is moving, and the other state when the motor is not. And so in your software, you'll be able to watch that output, and if you've set it to make a move, no matter how slow it is, this won't go true until the motor's completed its move, and it's ready to you're ready to move on to the next thing in your software. So for this demo, though, we can even without having any controller connected to it, we can override these inputs, and when we do that, we can control it with the software that we're running right now. And the first thing is the enable input, and right now, as I showed you, it turns freely. But when I engage the enable input, now it's in the servo mode. It didn't make a sound, but man, it really wants to stay where it is. I mean, I can force it to move a little bit, but it comes right back to where it was, and it really wants to stay there. And I'm not strong enough to actually turn that thing, but it's got plenty of torque. The next thing then, of course, is the directional input, but now that you've got it engaged, you can jog the motor and stop it wherever you want, or just give it little brief jogs, and it'll come right back to where it is. And you can also play with the speeds and so on. I can just increase the speed to 200 RPM. Whoops, that's a decimal point. 200 RPM, and now when I jog it, or we can play games here and go all the way to, well, we can, I don't know what the absolute limit is, but we can take it up to 2,000 RPM, and you can see that it spins really fast, and and then this acceleration is another thing to look at here. I have it at 40,000 RPM per second. If I go to a much more modest acceleration, let's just say 500 RPMs per second, now when I jog it, it speeds up slowly and stops slowly, and it's sort of like your car. If you got a load of groceries in a car, you're not going to be too heavy on the accelerator. But if you're on a drag strip, then you want to go back up to some big number here. There's 50,000, and now, if you're in a hurry, you can start the motor quick. So you got a lot of control over the motor, and you can program these numbers in, and you can disconnect it from the computer, but when you send it pulses, it will operate in exactly the way you've programmed it to operate. So it's pretty cool, and there's more features. I'll go over this more later, but if you click this button, you also get an oscilloscope. And the oscilloscope shows you, it can show you a lot of different things, how fast it's moving, what you've commanded it to move, and what it's actually moving, so there's a lot of information you can display on the oscilloscope. So if you're having problems with the way your system is moving, it's easy to analyze those problems with the oscilloscope. This one, it's off screen. I'd have to set the, but you can see it speeding up, running fast, and then slowing down again. So anyway, that's how the software, programming software, works. And in the next segment, we're going to take a look at controlling once the motors are programmed and ready to go, controlling them with software, and I'll go over a little bit what I'm doing in that respect. The next step now is to get the motors to operate under the control of a controller that'll be actually with them on the machine, and commanding them what to do and when to move and that kind of thing. And so for that we have to use the control inputs. You can see both of the motors are powered up now, and those blue wires connected to them are the control cables, and they plug into the second connector on the machine, and they will go to the controller that's actually going to give the commands to make the moves. The device I've chosen to run this operation is a microcontroller, a PIC controller, a product of a company called Microchip, and I'm using it in at the moment in what's called a development board. The development board is a product of a Swedish company, Microelectronica, and it has all the convenient inputs and outputs to allow you to, develop programs and so on for this this processor. You can see that the wires, the blue wires from the motors plug into the two of the I/O ports on the machine, and it's got a display on it too, and I eventually will be using that to just give some clues to myself when as to what state we're in and so on when the gear cutting is actually going on. Keep track of the tooth count. Reminds you to put the start out with the table in the home position and things like that. But right now I've just written the core of the software, which is really simple, and it just it sends out the pulses that you need and so on. And so the rest of the setup looks like this. I've got a really ancient laptop here, which I use to write the software. And then over here is a computer, another old laptop, and that one is running the software I showed you on the previous segment that we can use to tune the motors and set them up. So that's the rest of the setup there, and so now we'll take a quick look at the software itself. Here's a quick peek at the software. I just made a quickie flowchart here to show how it works. It's really very simple. I'm sure a 12-year-old kid, most of them could do a better job, but I chose, by the way, the microcontroller that I chose to pick was really based on my experience. I've used them for a long time, and I've developed a number of other projects with them. And so it just was familiar territory for me. I'm sure you could do this with an Arduino, and they're real popular right now, and they would easily do the same thing. The controller I'm using has got a lot more capacity than I need, but then again, I'm not going to make thousands of them, so it doesn't really matter. And like I say, Arduino would be capable of doing that. Lots and lots of other microcontrollers could do the job, or probably industrial controllers too, although I don't know too much about them. So anyway, the software is written actually in BASIC. I'm an old timer, so that's the one that I'm most familiar with. And this Microelectronica that I bought this development board from has a version of that their BASIC compiler that's free, so long as your programs don't get really large. And so I've been using the free compiler for a long time, and actually the version of the development board I'm using is I don't know, 5 or more years old, perhaps older than that, but it's called an Easy Pick 4. I think they're up to 6 or 7 or 8 now. I've used this old laptop and the Easy Pick 4 here for a long time, and it works out fine for me. So looking at my flow chart here, starting from reset, the first thing we do is enable the motors, and then we set the value of the variable count, and that variable is just is the number of pulses you want to put into the motor. And so based on, if you take the number of pulses and the resolution that I showed you yesterday on the or in the earlier session on the motor, and then you know how far you want to move, then that's the number of counts you'll use. So you set that value, and and you also set the direction of the motor. The A input there, high or low, sets the direction of the motor, and then you jump over to a subroutine, and that subroutine is on the right hand side, and entering that subroutine, the first thing you do is you take the pulse input for the motor and set it true, and then set it false, 1 and 0, and then you decrement the count variable, and you then ask the question, is the count reached 0 yet? And if the answer is no, then it goes back up here and sets the pulse true and false again. So basically, every time you go around the loop, you have one pulse that comes out. It goes, the value goes high and then goes low again, and that's a complete pulse. Now, when the count does get to 0, now the next step is you wait for the end of move signal from the motor. Yesterday I was telling you there was an output from the motor which was end of move, and you wait for that to happen, and once that happens, you return from the software. So then back on the left hand column here, after you do that, then I put a delay in there, mainly just so I can watch to see how the motors are working. I may not keep that in there in the final version, but anyway, then you change the direction of the motor, and you also change the speed of this. This will be motor 1. You'll change the direction and the speed of motor 1, which just amounts to change the direction, you take the A input to its opposite state, and to change the speed, you just take the enable input and you drop it for a few milliseconds and then bring it back up again, and that'll change the speed of the motor to the alternate speed. And then from there, now you go back and run the subroutine again. So you go back to the same subroutine, but this time you've changed the speed and the direction, so it'll make the motor run in the opposite direction and faster, generally. In my case, faster. Could be either way. And then another delay, and you set the count again, and now you go to a subroutine that's designed for motor 2. I don't have that on here, but it's essentially the same one as the one for motor 1, but it just has different output pins and that it connects to. And then when that's complete, then you loop back to the beginning and you start the process all over again. Now in the final software, there'll be a counter in there that'll count the number of teeth you've already done, and when you've finished the gear, it'll stop. But for now, I've just got the core of the software, and I want to make sure I'm happy with that before I add any more bells and whistles. Okay, now we've got the motors ready to run under control of the little software program I have on the development board. And if I push a button on this board, it'll start the routine running. Now you see the motor on the left is supposed to represent the one that will be driving the table, and you can see it moves slowly in one direction to do the cutting of the gear, and then speeds back to get ready for the next stroke. It's moving around now, and now this would be moving the table back. Now you can see the other motor is set up to advance the rotary table to the next gear tooth, and so right now it's making that turn, and now the table moves to the right and back to the left, and now the gear advances another tooth. So this is the basic part of the software that will run the table, and once we get it all mounted to the equipment, we'll have adjustments in the amount that each motor will turn and the speed and all those things, but the basis is here. Okay, so now if we take a look back at the Technic software. I have that plugged into the back of the left-hand motor. I've got a cable there that goes to a computer that we can use to run the Technic software, and it'll actually tell us what's going on with the motor. Okay, this is the same screen we showed in an earlier section of the video, but here we're looking at what's actually happening with the motors when they're being controlled by the my PIC controller. You can see the directional light going on and off in the center of the here you can see the directional light going on and off as the direction changes. You can see the alternate speed light go on and off. When it goes faster, the alternate speed light comes on, and you can actually tie that in with the scope, which we'll do in a second. But one of the things I wanted you to notice particularly is this the blue box on the right hand side, which tells you that the motor is moving when the light is off, and when the light is on, the move is complete. So that's the line that I'm monitoring to the output from the motor that I'm monitoring to tell my software what's going on. Okay, I'm going to back up here a little bit, and you can see that the scope now is showing the position of the motor. It's just exactly where it is in its rotation cycle, and you can see that starting from the left, the motor goes counterclockwise in a slow direction and then goes clockwise in a rapid direction. And you can see how that ties in with the indicator lights above that. They'll tell you the alternate direction light is on when it's going up, and it's off when it's going down, and the alternate speed light goes on briefly too. So I'm sorry, the alternate direction is on when the motor is going counterclockwise, and off when it's going clockwise. So that gives you an indication of that. And then down in the bottom, it actually tells you exactly what position the sensor in the motor is in. You can see this this number here. It starts at -116, and when it reaches the end of its move, it's up to 6,500. Okay, so it's showing you what the counter in the motor is actually recording. And we'll zero in on the scope a little more now, and you can see that not only position, there's a lot of other things that you can watch too. This one, we'll just kick this down, and there's velocity is what I want here. Actual velocity. So this will be the speed of the motor at any one instant of time. And you got to wait till it sinks here. On the next shot, it should sink. There we go. Now it's moving in the counterclockwise direction, and it stops, and then it moves in the clockwise direction. And again, that ties in with the lights up above. So you could use the scope traces to play around with the way the motor operates. You can adjust the acceleration. You can adjust that RAS factor until you get the performance you want. I took the position readout that we had a second ago, and I expanded it dramatically so that I could see exactly what happened when the motor stopped, and because I don't want to have any overshoot there. And by playing around with the RAS and the and the acceleration, I got that to be essentially 0. So so there's but you can, like I say, you can expand the scale so you can see in more detail what's going on at transition points. So you can get a lot of information. So we've got the motors working now. We got them operating on the bench. Of course, they're completely unloaded, so there's no you know, there's the behavior of the motors is not going to be like it is when they're driving a heavy load. In fact, there's one of the features of this motor is an auto tune function. Servo motors have to be tuned for the, you know, depending on the mass that they're turning. If you got something that's really big, heavy wheel that they're trying to turn, or depending on the friction that you're trying to drive, they have to be adjusted so that they operate correctly in different conditions. And they have an auto tune function, which I've tried on the motors as they are, but like I say, they got essentially they're not driving anything right now, and so the auto tune really didn't make any change in the way they operated. But when we get them connected to the machinery, why you're going to have to retune them to make them optimized for that particular job. And so the next step for me is going to be to take the electronics, this demo board or development board that I have wouldn't last 5 minutes with chips raining all over it from my vertical mill. So I'm going to take the electronics and repackage it, put it in a box so that will shield it from that. Not this development board. I'll use a smaller board that has most of what I want on it. And also make some device, or some brackets, I guess you'd say, to mount the motors on the machine table, and get that set up. And I'll show you how that works. I'll do that, and then we'll see if we can get the system to drive the loads that it needs to do in order to make gears. So I'm going to put a link to the Technic webpage on the ClearPath motor at the description of this video, and I'll also put a link to Microelectronica and a link to the data sheet for the processor that I'm using. So that's all for this video, and I'll be back soon with the next step. Thanks for watching.